The plan was straightforward. Lock China's semiconductor progress at around the 14-nanometer level, cut off access to EUV machines, isolate the supply chain, and preserve the technological gap. Clean, logical, almost airtight. Then, in 2023, Huawei introduced a 7-nanometer processor, and just like that, the story stopped being about a single piece of equipment and started becoming something far more complicated. Because in the world of chip manufacturing, EUV systems built by ASML were treated almost like untouchable artifacts, machines so complex they couldn't realistically be reproduced without decades of shared expertise across Europe, Japan, and the United States. Each scanner contains over 100,000 individual parts, optics engineered to atomic precision, lasers powerful enough to strike molten tin droplets tens of thousands of times per second, mirrors so flawless they can detect imperfections smaller than a virus. For years, the belief in Washington and Edelfone was simple. No one could catch up quickly, especially not under heavy sanctions. On paper, that assumption made sense. China couldn't purchase EUV systems. The Dutch government halted exports in 2019 under U.S. pressure. Then came restrictions on advanced AI chips, followed by limits on manufacturing tools and design software. Each layer tightening the grip further. The goal wasn't just to slow China, it was to make progress so difficult that entire industries would struggle to breathe. But something unexpected happened. Instead of collapsing, China reorganized. Companies like SMIC and Huawei, alongside state-backed labs, came to a hard conclusion. If EUV lithography was out of reach, the problem needed to be approached from entirely different angles. Not cleanly, not efficiently, but persistently. Hundreds of engineers across disciplines, optics, plasma physics, material science, computational modeling, chip packaging, began tackling fragments of the challenge independently. Later, those fragments were pieced together into something functional. That shift matters more than it seems. And the semiconductor industry has always relied on specialization. One company focuses on lithography, another manufactures chips, another designs architectures, each stays within its lane. China looked at that system and asked a different question. What happens if those boundaries start to blur? That's why intelligence reports began focusing less on hardware leaks and more on knowledge networks. The concern wasn't just about stolen technology, it was about a structural shift. China had stopped treating semiconductors as a purely commercial industry and started treating them as strategic infrastructure closer to a space program or a nuclear project. Different priorities, longer timelines. There's a detail buried in a late 2024 report that didn't get much attention. Even as sanctions intensified, Chinese semiconductor firms increased their reliance on domestic suppliers. At first glance, that seems counterintuitive, but the restrictions forced companies to adopt imperfect local tools sooner than they otherwise would have. Painful in the short term, but potentially transformative over time. While reports in the West focused on slowing China's AI ambitions, China quietly expanded its engineering pipeline, graduating more semiconductor specialists than the US and Europe combined. Not exactly a minor factor. To be clear, China hasn't matched ASML in pure technical capability. Claims of a fully replicated EUV system are exaggerated at best. But that's not the real issue. The more subtle and potentially more significant shift is that China may not need to follow the same path to weaken ASML's advantage. Once enough workarounds accumulate, the monopoly changes shape. Advanced EUV multi-patterning chiplet-based designs, AI-driven yield improvements, domestic materials and tools. None of these individually replace EUV, but together they reduce dependence enough to keep moving forward. At that point, the technology stops acting like a wall and starts behaving more like a tax, costly, inconvenient, but survivable. And this is where those 300 engineers come into focus. Not because they solved EUV lithography outright, They didn't. And the real breakthrough was realizing that large-scale industrial coordination still works if a system is willing to tolerate inefficiency long enough. It's easy to imagine EUV as a single, impossible invention, a moment of genius. In reality, it's the result of decades of incremental precision, stacked layer upon layer, until replication becomes overwhelmingly complex. China recognized that and stopped trying to copy it directly. Instead of chasing perfection, they built resilience around its absence. Multi-patterning techniques extended the life of older lithography. Advanced packaging increased performance through design. AI-assisted corrections compensated for hardware limitations. Individually imperfect, collectively effective. A teardown of Huawei's Mate 60 Pro in 2023 revealed a processor manufactured at roughly a 7-nanometer class node, despite restrictions explicitly designed to prevent that. Debates followed. Were the yields sustainable? Was it truly 7 nanometers? Did the economics make sense? All valid questions. But geopolitically, something else mattered more. The chip existed. That alone proved the central objective of the sanctions freezing progress had not been fully achieved. Behind that result wasn't a dramatic breakthrough. It was something far less glamorous. Endless coordination. Suppliers adapting to missing materials. Engineers redesigning around unavailable components, universities testing alternatives under unstable conditions, government funding, absorbing losses that private investors wouldn't accept. This wasn't innovation in the cinematic sense. It was endurance. Semiconductor manufacturing has always been fragile. One contaminated component can destroy entire batches. One misalignment can ruin production. It's a system built on precision and paranoia. The real miracle is that modern chips exist at all. China's response to sanctions revealed something uncomfortable. When perfection is out of reach, increasing the speed of iteration can change the equation. Western policies assume progress would stall in a predictable, linear way. But engineering systems under pressure don't always behave linearly. Sometimes they evolve. There's historical precedent. In the 20th century, rigid systems struggled to keep pace with flexible innovation models. China studied that history and chose a different approach. Messy, overlapping networks of state labs, private firms, universities, and regional initiatives. Inefficient, yes, but adaptive. And then came the reversal. Before 2019, Chinese companies often preferred foreign tools because they were superior. After sanctions, that choice disappeared. Domestic suppliers suddenly had guaranteed demand, financial backing, and most importantly, real-world deployment that accelerates learning in ways theory cannot. Even ASML leadership warned about this dynamic early on. Restrict access long enough, and a market as large as China will begin rebuilding the entire ecosystem internally. Slowly, painfully, but steadily. This doesn't necessarily end with China replicating EUV machine for machine. The deeper shift may be structural. A world dividing into parallel semiconductor ecosystems, one optimized for peak efficiency and the other for strategic resilience. Different goals, different trade-offs, and those 300 engineers weren't part of a single secret lab. They represented overlapping teams working on interconnected problems, light sources, mirrors, plasma control, precision systems, fragments, and EUV itself is a system of fragments. ASML's dominance didn't come from a single breakthrough, but from decades of collaboration across specialized industries. Geopolitics disrupted that network and unintentionally encouraged China to attempt building its own. One of the hardest challenges wasn't generating EUV light. It was maintaining stability across the entire system at production scale. Tiny disturbances can destroy precision. This is where another shift emerges: software. Instead of relying entirely on perfect hardware, Chinese firms increasingly use computational methods to correct imperfections. AI models predict defects, optimize processes, and improve yields. In simple terms, they're converting computing power into manufacturing precision, and that changes the game. Restrictions focused heavily on hardware, machines, chips, tools. China responded by strengthening less visible layers, algorithms, materials, process engineering. Harder to measure, harder to block. Meanwhile, China's system tolerates inefficiency differently. Lower yields, higher costs, and acceptable trade-offs if they build long-term capability. In that context, early failures still serve a purpose. Training, infrastructure, experience. The global semiconductor industry spent decades optimizing for efficiency. Now the question is shifting. What if resilience matters more? China may not achieve complete independence anytime soon. Some technologies remain extremely difficult to replicate, but the timeline assumptions may have been wrong. Isolation doesn't always weaken a system. Sometimes it accelerates adaptation. ASML built one of the most advanced machines in history, but the strategic belief surrounding it, that it created a permanent barrier, may have been flawed, because what one side saw as an unbreakable moat, the other saw as a coordination challenge. That doesn't mean China has won. There are still major gaps, but something fundamental has changed. Before 2019, reliance on Western semiconductor infrastructure was widely accepted. After sanctions, it became a vulnerability. And once a nation redefines dependence as a risk, priorities shift. Investment patterns change, education systems adapt, industries reorganize. Semiconductors stop being just products and become symbols of sovereignty. That shift alone alters the trajectory. Technological choke points work best when reintegration feels possible. And when that belief disappears, adaptation begins, slowly at first, and then unevenly, then all at once. The semiconductor world of the 2030s may look very different from today. Less unified, more fragmented, one system chasing absolute performance, another focused on survivability under pressure. No